Hello everyone, this is Afnan Al-Bahli, a PhD student in Department of Computer Science of University of Denver. Today I'm presenting a paper titled Model-Based Testing of Smart Home Systems using EFSM and CEFSM as part of my thesis, which tests smart homes systems. The outline of this presentation is as you see. Introduction with research questions. A background has a definition of model-based testing, finite state machine, and extended finite state machine, and communicating extended finite state machine with works done in this area. Then I'll be introducing our approach and express that with a case study. Then conclusion. The term Internet of Things, IoT, was coined by a member of the radio frequency identification development community in 1999 and has become widely used over the past decade. IoT has many definitions. A common one defines it as a network of physical objects. This network is not only consisting of computers, but it can consist of many types and sizes of devices, such as smartphones, people, appliances, medical tools, vehicles, and even places and buildings. One common definition of IoT is a combination of devices connected together and data shared between those devices via a platform. The number of devices connected to the Internet increasing rapidly. By 2025, there will be 75 billion IoT devices globally. Smart home is one of the key applications of IoT, but it's not the only one. Smart cities, wearable devices, smart vehicles, and connected health are other examples of IoT applications. But why do we say that smart home is the key application of IoT? Because by 2020, 41% of the IoT devices are installed within a smart home. With this massive number of connected devices to the Internet and the expectations of that number to increase rapidly, software developers and researchers are concerned about the reliability and availability of these devices. Therefore, it's necessary to guarantee that these devices are functioning well. Testing IoT system and applications, it's different than testing any software due to the interaction between softwares and physical components in IoT environment. Heterogeneous systems management is another issue due to rapid growth of the different types of connected devices. Interoperability is another issue, as heterogeneous systems differ in operating system, programming languages, and hardware. All this are lead to challenges for testing. In IoT, we need several levels of testing. The first of these is component level testing for each device connected to the Internet. Next, integration testing is necessary for reliable device interaction. Finally, system level testing is needed via testing of the controller of the entire smart home system, which is usually a smartphone application. In this paper, we will have 3 research questions. First of all, is it possible to develop black box models for modeling device behavior and device interaction? Can we develop a model that is hierarchical and scales? Can we develop a model-based testing technique for these models that includes testing criteria and can be used for device testing, device interaction testing, and system testing? What is a model-based testing? It is a black box testing technique that generates test cases from a model of the system under test. It has many advantages. Some of them are test cases can be generated automatically, so we are not doing that manually. Testing the system under test earlier in the software development lifecycle will save cost and time and improve testing quality as well. Several graph-based models exist, such as finite state machine. This is a traditional method to model software applications and systems. Many researchers use this method to develop different kind of systems. For example, Harrison used it to model distributed system, while Andrews introduced FSM Web to test web applications, and also propose an approach for regression testing for those applications. Al-Haddad used FSM to introduce FSM App, which is an extension of FSM Web to test mobile applications. But this method has its limitations. For example, it's limited because of the parallelism, which make it not very suitable to model the behavior of IoT systems, which consist of devices working in parallel. Another way to model your system is using extended finite state machine or communicating extended finite state machine. EFSM is an extension of the FSM introduced to overcome the major shortages of FSM. Abdul Jawad et al. Model a real-time adaptive motion planning system using EFSM. CEFSM is added a communication channel between EFSM to allow communication. Lee and Wang introduced an automatic test generation methodology from system specification modeled with CEFSM, while Hessel and Peterson propose a global algorithm to generate all feasible test paths from CEFSM. Portfire propose an incremental technique to generate, test, and execute them for communication protocols modeled by CEFSM. In this section, we introduce a new systematic testing methodology. The proposed methodology is a model-based testing technique to test the functionality of a smart home system that uses IoT. Model-based testing employs extended finite state machine and communicating extended finite state machine to model the smart home system. This methodology consists of three main phases. Each phase is modeled and described in details in the coming slides. Phase 1, building the model. We build the model by first identify the smart home system components, then construct the behavior model for each device, then construct the behavior model for the possible interaction between the devices. In phase 2, we generate test paths. First of all, we generate test path for each device of the system, then for the interaction between the devices. In the final phase, we aggregate and linearize the generated test paths by test path aggregation first using all combination, then test path linearization. In this phase, we will identify different components in the smart home system. So, a smart home system consists of users, which in this case, the homeowner, who can add or delete devices in the smart home, and who could assign different roles for different people who can access this smart home system. Another component is the mobile application. Mobile application where you can control the devices installed in your home. It can be a single mobile application that controls the entire house, or it can be different mobile application, depends on the type of devices that you have and how they're compatible. A third component in your smart home is the smart devices. Smart devices can vary between smart lights, smart thermostat, garage opener, bill, and etc. Each of these devices consist of a sensor that sense the data in a specific area, then send this data to a controller who has a pre-installed thresholds in it. So based on the received data from the sensor, a controller can decide what to do, what action need to be done for this device, and send this result to an actuator which can act based on the received data. Another component in your smart home is a standalone sensor. A standalone sensor is different than the sensor inside the device itself. This can be installed separately in the smart home. And finally, the physical switches, which is the one in the wall to turn on and off the light. And in the specification, we will assume that those physical switch on all the time. After identifying the components in your smart home, we need to construct a behavior model for each component using extended finite state machine. This is to model individual components of the device, for example, sensor, controller, and actuator. Then we use CEFSM to model the device itself. And finally, we construct a behavior model for the possible interaction between components using communicating extended finite state machine. At this phase, we will generate test paths using any graph coverage criteria, but in this paper, we choose edge coverage and apply it for each EFSM component model in phase 1. Next, we're going to use edge pair coverage to cover the interaction of each pair of devices. This is going to be looked in detail in this case study. Last phase is aggregate and linearized generated paths. We will use all combination technique to aggregate the generated test paths. Then we're going to decide how to linearize each combination of test paths that are executed in parallel. A sequential execution of these commands need to be determined while maintaining order of commands execution within the same components. In this case study, the smart home consists of 3 smart devices, namely smart lights, thermostat, and smart curtains. Based on the specifications and requirements, we build the behavior models for these devices. Sensor model, as presented, consists of 2 states represented with the nodes S1 and S2, which is off and on. And the transition between those nodes are T1 and T2. Controller model represented by 4 states. Initial state S3, which is the controller is ready. S4, where the controller need to check a threshold defined. To decide, go to state 5 or state 6 based on the decision done in S4. And the transition between them I'm going to explain later. Actuator model is also consists of 2 states, S7 and S8, and the transition between them are T8 and T9. The device itself is modeled by connecting the sensor, controller, and actuator with messages. That is a CEFSM. For example, sensor and controller, after the sense data has been sensed with the sensor, it's sent via M11 to the controller. And the decision made by the controller sent via message M12 to the actuator. A possible interaction between the devices is displayed in the second graph by showing 2 devices connected with 2 messages, M4 and M5, to send the status of each devices. Transitions between the devices component, EFSM transition, which is the sensor, controller, and actuator, is presented in this table. For example, transition 1 between state off and on of the sensor will have a state off as initial state, will has a condition that the signal is on to turn the sensor on. Move to transition to state 2. T2 is the other way around. You start with on state, then when you receive a signal equal off, you turn off the sensor. Same thing to the controller and actuator. The transitions of device CEFSM is represented in this table. T1, for example, is different from previous table because now we have a message sent between the sensor and controller. This is M11. So if the state start with off and we receive a signal equal on, then the sensor gonna be on, and a message sent to the controller with the sensed data, and so on for the other transitions based on messages that has been sent. For example, T4, when the controller check whatever threshold he has moved to, make him move to S6, and it's gonna send message M12 to the actuator asking them to turn the device on, or as T6, turn the device off. Finally, the device interaction CEFSM transitions is represented in this table. This time we're gonna add M4 and M5. M4 will be in transition 8 in the actuator. When the actuator is off and receive the command to turn it on, it's going to be turned on and send message M4 of the status of device 1 to device 2. While T8 of the device 2, when the command equal on, turn the device on, it's going to send the status of device 2 to device 1. After modeling all these devices, we need now to generate test paths. We will use, as we mentioned in our approach, we will use edge coverage. That means we need to visit each transition in the graph. For example, sensor has two transitions, T1 and T2. To visit them both, we need to go from state 1 to state 2. That covers transition 1. Then we go from state 2 to state 1. That covers transition 2. Same thing done for the controller and actuator. This is lead us to 4 transitions, 4 test paths, TB1, TB2, 3, and 4. Test path generated from device modeled by CEFSM, and this time we're going to use each pair coverage. So we're going to have device test path 1 from the sensor to the controller, and device test path 2 from controller to actuator. Test path generated from device interaction modeled by CEFSM. Again, we're going to use each pair coverage. In this case, device interaction TB1 is all what we have, which is moving from device 1 to device 2, going back to device 1. That covers all the transitions between the devices. In this phase, we need to determine a way to serialize each group of test paths that work in parallel. Serialization basically execute a full path of an individual components with each different all combination of commands in the combined paths of the other components. To illustrate this process, let us consider device interaction test path 1 from the previous table. It is device 1, device 2, device 1. So in this case, we will start by generating all possible combination of test paths for these devices. So for device 1, we're going to have to choose between TB1, TB2, TB4, TB1, TB3, TB4. But this is going to result in 8 test paths for all combination. Determining which device is going to be executed first is done by the serialization, and this is what we have at this stage. In conclusion, this paper presents a method to test a smart home system using IoT. Our approach is a model-based testing approach. It used extended finite state machine and communicating extended finite state machine to model the smart home system. At the end of this paper, we were able to generate test paths on component level and integration level. That's all what we have today. Thank you for your listening.